metals. So if you have a compound made up of nitrogen and oxygen, for instance, that is not an ionic compound. That's not making a cation and an anion. That's doing something else. And we're going to talk tonight about what that something else is, like what makes it different. But the first part that we'll do is just talking about how to name them and how that's a little bit different from the naming stuff we've already talked about. So let's say we have a compound of nitrogen and oxygen. Well, there are actually several compounds that nitrogen and oxygen make with each other. There's N2O. Anybody know what that one is? Yeah, the like nitrous oxide. But there's also NO. There's NO2. There's N2O4. There is N2O5. There's a bunch of them. So we'll list a few of them there. And if we were to name that by some sort of rule, like with the metals and nonmetals, it wouldn't really make sense. Like we could have nitrogen with all these different charges, but it's not really an ion. So we need a way to actually name these separately that is clear. And the way that it works is you simply say how many of each element you have using a prefix. And here's the list of prefixes that we're going to use. Mono is 1. Di is 2. Tri is 3. Tetra is 4. Penta 5. And hexa is 6. We're not going to go higher than 6. So to name the compound N2O, we would say dinitrogen monoxide, to show that we have 2 nitrogens and 1 oxygen. Now we also know that that compound is called nitrous oxide, or some of you may know that. A lot of molecules have these kind of common names that we call them, or older names, older ways they were named before this systematic thing was in place. And if you're really working with a lot of chemicals, you got to kind of know both of them. But if you call something dinitrogen monoxide, if you're looking up safety information for dinitrogen monoxide, you know it's always going to come up. It's always going to be the right name. All right, so one other thing that you might have noticed there, because of the 2 O's that would be together, it's not mono-oxide, it's just monoxide. So one of those oxygens gets dropped, or one of those O's gets dropped there just to make it sound better. So what do you think NO is then, given this system? Nope, that's actually what N2O is. That's the other name for that. What would you call just NO?
Mononitrogen monoxide?
Yeah, mononitrogen monoxide. One other thing that happens in this naming system is when there's a mono on the first one, because that's so common, we just leave it off. So this actually becomes nitrogen monoxide. Just because it's so common.
Oh.
So like if you were to look in a chemical catalog that was alphabetized or something, there would be like half of it would be the M's, because everything would start with mono, because a lot of compounds have 1 of something. So you just leave that off and call it nitrogen monoxide. What do you think the next one is? Yeah, nitrogen dioxide. What about N2O4? Yeah, dinitrogen tetroxide. So the A is dropped, right? Whoa, what's going on over here? Okay. The A is dropped. If you leave that in, that's just like to make it better. I don't know. If you leave it in, I wouldn't mark it wrong. You know, I don't think that's a really important part of the naming, but yeah, it is dropped. And then N2O5 would be, yeah, dinitrogen pentoxide. So most people like this system compared to the other ones. Much nicer. There's not all that calculating of charges and whatever. The danger of that is that you want to name everything using this system. But this is only appropriate for when you have two non-metals. The metals are in there. You got to go back to the other rules that we worked on before. And that's a danger as these other exams come up, when there will be all kinds of different compounds on them, and you want to write this kind of a naming for everything. So let's practice this. Name these three compounds.
These would never be a negative, right?
What do you mean?
Well, I was just looking back at the ones that we had to remember, the ionic compounds.
Oh, yeah, right.
Because they kind of look alike.
Right. These are all neutral compounds. Those would still have metals in them, would still have ions in them. Yeah. Got some names? Some names might not be right. Something. What do you think the first one is? Yeah. So one thing with this, when as you notice with the oxygen, that it goes to oxide. So we still use that kind of ionic ending on the name, even with these prefixes, and even though these aren't actually ionic compounds. So this would be sulfur hexafluoride. 6 fluorines, hexafluoride.
You drop the mono on each one that's in the front? I thought it was just one.
Right. Nope. Whenever there's just one in the front, you drop the mono. What about that middle one? Yeah, carbon monoxide. And then the third one? Right. Okay, so be careful. This one was kind of a trick. This is an ionic compound. This is the old style one because it's got a metal and a non-metal. So you can't call that dipotassium monoxide or something like that because it's not covalent. We have to go back to the old names that we did last time and call it potassium oxide. Nothing in parentheses because it's a known constant charge over in group 1A. Yeah.
Do they do that naming just to help you like differentiate between covalent and ionic bonds, or is there like a special reason behind it?
Mostly.
Because Is it just like a way to help clear up with language?
Yeah, it's just a way to be like systematic about it and to show what's actually going on in the compound. Now, that said, if you look these compounds up, like in safety data or something, they're often cross-listed. So something like K2O might actually be listed as dipotassium monoxide on some database just because they want to avoid any confusion. But according to the official rules that we use, that's what it should be named. The other reason is that, as we'll see when we move on and talk more about molecules and stuff, it makes more sense to name these things using this way, whereas the metals, it doesn't make as much sense because ionic compounds are built in a different way. And so you're not describing the actual physical, like what it is as much,
So
I guess.
Yeah.
Yeah. Okay, so now we know the naming. Let's look at what these things actually are. So these are compounds that are made up of something called covalent bonds. And let's look at what those are. If you have a, yeah, go ahead. Right. So let's say you have a hydrogen atom. We can show that it has one valence electron by drawing a little dot next to it. This is technically called a Lewis dot structure. I don't know why it really needs a special name. It's just got a dot there to show that it has one electron. If it had 7 valence electrons, we draw 7 dots. That's all that is. So seeing hydrogen with its one valence electron, we know that there are 2 ways that we've talked about so far that it can satisfy its full bucket, empty bucket rule. What are the 2 ways that it could do that? It could lose an electron and become H+, and then it would have an empty bucket. Or it could gain an electron and become H- and have a full 2-electron bucket. So we've talked about those 2. And those both mean that it becomes an ion, either a cation or an anion. But there's actually a 3rd way that it can fill its bucket, and that is to share its electron with another atom that also needs to do the same thing. So if we imagine another hydrogen atom next to it, if those atoms get close enough together, then those electrons actually exist in each other's valences at the same time. So if you imagine the valence shells as these like spheres, if you put 2 hydrogen atoms close enough together, those spheres will overlap. So that means that the electrons can literally exist in both atoms' valences at the same time because they're overlapping. And so that's where you get this thing called a covalent bond. Co means like together, and valent, the valence shells. So the valence shells are together. And the way we express that, we can do it 2 different ways. We can do it in dots. And we can show that each hydrogen brings 1 electron to the party, but then they get to share both of them. And so now when we count the valences of, we count the valence electrons of atoms that are in a molecule like this, we count them for both atoms. So we say this hydrogen has 2 valence electrons, and this is within the structure. But then this one does too. While it's bound together, that's also going to have 2 valence electrons. So in that way, we've satisfied both valences as long as those hydrogens stay close enough together to keep sharing those electrons. As soon as they break apart, that doesn't work anymore. And this is where we get the hydrogen molecule. So another way to write this is to draw a line in between those. And you've probably seen that line before in these structures, but that line has a really specific and important meaning. It represents 2 shared electrons. So we don't use lines when we talk about ionic compounds, because that line only makes sense in the context of shared electrons. Okay. So let's see what happens when we get to slightly larger molecules then. Or not larger, but larger atoms. So let's take like chlorine, for instance. How many valence electrons does chlorine have? 7. So we would draw 7 dots. And in a way, yeah.
Sorry, really quickly, because actually when I was like reading the book, I'll be honest with you, this is kind of where I was fine at that first part, but then come this next part, I kind of lost it because as you start to like go on,
Yeah.
does it matter what order you put the dots?
No.
So I mean, you could like literally put them in any order you want as long
Yep.
as you keep them in twos or.
Even that, I would say, is not that important. As long as there's 7 of them, that's what's important.
Okay.
We usually put them in 2s because then it's really easy to see like which one's missing or which ones are missing, because you know it's got to be 8. And if they were just kind of randomly distributed, you have to like count them every time.
Okay.
But as long as there's 7, I mean, there's 7. That should be okay. Yeah. So chlorine's in a similar position to hydrogen, that it's 1 electron away from a full, what we call an octet, full 8 electrons in its valence shell. So it can gain an electron and become a chloride ion. We've already talked about that. Or it can share an electron with another atom and become a molecule. And one atom that could do that with is itself, another chloride ion or another chlorine atom. And I'm going to draw this kind of opposite as the other one just so we can see that they fit in each other's spots. But you could, again, draw this however you want and show that those 2 electrons can be shared, making a chlorine or dichlorine molecule. And now again, when we count the electrons on that chlorine that's in that molecule, we count those shared electrons for both atoms. So we would say this one now has 8, and this one has 8 too. And that way that's fulfilled. We could also draw it with a line. And sometimes we actually leave those other electrons on there to show that they're there, to be specific. If you go on and take organic chemistry or something, you'll do a lot more with that because it's important to track exactly where the electrons are going all the time. But basically, that's the same thing. So that's what we call a chlorine molecule. Because of this, we see that several nonmetals on the periodic table always exist by themselves as a double. So like hydrogen is never just H atoms floating around. It's always H2 molecules because of exactly this. Because an H atom by itself is not stable because it has that half bucket. It has that unpaired electron. And if it can join with another hydrogen atom, then it's going to be a lot more stable. So that gives rise to what we call the diatomic elements. Di meaning 2, so 2 atom elements. Elements that always exist as a double. And they are H2, N2, whoop, not C2, sorry. 2N2, O2, and the rest of that column as well. And you should know those. They won't be important exactly in this chapter, but in the next chapter, when we start writing chemical equations, you need to know if it says hydrogen reacts with oxygen and you want to write that down, you got to know to write down H2 plus O2, not H plus O. Because it will actually change what happens in the reaction. So know that these H always exists as a double. Let's look at oxygen, for instance. We can do the same exercise with oxygen. How many valence electrons does it have? 6. So we pair it with another oxygen, share electrons, and get O2. There's a problem here. Anybody see the problem? Yeah, we still don't have 8 electrons per oxygen there. We only have 7. So what's the solution? Yeah, we have to share 2 pairs of electrons instead of just 1. So oxygen will share 2 pairs of electrons. And the way that we draw that is with 2 lines to show that there's actually 4 electrons being shared. So when we count that up, we say, all right, this oxygen has 2, 4, 6, 8 electrons around it. And this one has 2, 4, 6, 8 around it. And in a later chapter, we're going to go back to this and talk about how to draw all these different structures of different kinds of molecules. But you can kind of see how this starts to work. If we take that oxygen again with its 6 valence electrons, instead of joining it with itself, we could join it with something else, like hydrogen. And we could imagine making those shared pairs with 2 different hydrogen atoms.
Why would it be 2 hydrogens?
Because if it just did 1, it wouldn't be up to 8 electrons. There would still just be that one unpaired one, lonely one sitting there. So we need 2 of them to fill it all up. You see how if you count it up now, you've got 2, 4, 6, 8 on the oxygen, and 2 on each hydrogen. And this is, anybody know what this molecule is?
H2O.
Yeah, H2O, this is water. So that's why water bonds in the way that it does, 2 hydrogens to 1 oxygen, is so they can all share these electrons and be stable in that way.
So whenever you do a diagram though, using like hydrogen, oh wait a second though, but oxygen is always 2, 2. Yeah, I don't know.
Okay.
It's so funny, because like this is truly like last night, like when I was like reading it, this is totally where I started to get lost. Like I had it
Okay.
up until now.
Okay.
Because O is always 2 as well, I thought.
What do you mean 2?
Well, because you said like the diatomic elements,
Yeah.
so they always exist like with the double, meaning so that there would be 2 O's and 2 H's.
When they're by themselves. So if other atoms come in, then they can just do whatever they need to do.
Okay.
But when oxygen is just by itself, it's going to be O2. There's going to be 2 atoms bound together in a molecule.
Okay.
All right, so this comes a little bit later, but if we imagine O2, the molecule, reacts with H2, the molecule, and you actually need 2 of these molecules, and that will form 2 water molecules. So that's how that reaction works, for example. And we'll come back to that in the next chapter. So you've got oxygen by itself and hydrogen by itself, but then when they all combine, they kind of split up, and 2 of the hydrogens go with each oxygen. But for now, the important part is to see that you can join these things together, and then a molecule or an atom like this is happy. It does have its full bucket because you count these 2, but then also these 2 shared and these 2 shared. And those all count toward oxygen's bucket. All right? That's a good place to take a break. So let's take a break. We'll come back. We'll talk about polarity and practice this a little bit.
Keep our tests.
Yeah, keep your tests. All right, let me pull up the book here because we need some pictures.
He's like poking you with this. All right.
I really like a good floor nap. I don't know. If that's weird. Yeah, we just lay down on the floor and sleep for a while.
Yeah.
Yeah.
I'm all right with that.
Just push our exam off.
You can just keep lecturing for those of us who can, learn our sleep.
Yeah. You can just learn in your sleep.
Everybody else will just watch later on when we get home.
The only problem with floor naps is your arms end up falling asleep because either they're underneath you or they're like on top, and then you wake up and you're like,
Or you lay on your back.
I have no arms. Yeah.
Or you-
Yeah, but then if your arms are like up here, they still, I don't know.
But you always wake up sore in the morning. Yeah.
Yeah, sure.
Regardless.
All right, let's talk about this stuff. Okay, so we got our covalent bonds put together. All the covalent bonds that we've seen have equal sharing of electrons. So like if you imagine two hydrogen atoms sharing 2 electrons, those electrons are going to be pretty much evenly shared between the two. Put them wherever you want, and you can imagine they're kind of evenly shared among that whole sphere. There's no reason to be more on one side than another because it's totally symmetric. But in other molecules, that's not the case. So if we looked at something like HF, would look like this. Sorry, getting lazy with my electrons here. It would look something like this. But those 2 electrons in that bond would not be shared evenly. And what would happen is they would be pulled more toward the fluorine. So these 2 electrons would kind of get like pulled this way toward the fluorine. So you'd have a lopsided sharing of electrons. The fluorine would have it for more, and the hydrogen would have it less. And because electrons are negatively charged, what does that mean in terms of like negative or positive charges on the molecule?
So fluorine will be more negative and more positive.
Right, exactly. So because the electrons are spending more time around the fluorine is going to have somewhat of a negative charge, whereas the hydrogen is going to have somewhat of a positive charge because of the extra electrons over toward the fluorine. Now, we don't write like plus or minus because we reserve that for ions. What we do instead is we say it's a little bit plus, it's a little bit minus. And the symbol we use for a little bit is the Greek letter delta. So we say this side is a delta minus and this side is a delta plus. So a little bit minus on that side, a little bit plus on the other side. If you haven't seen that letter before, it looks like this.
So is that just part of the 8?
Yeah, it's like part of an 8, but it's kind of smaller on the bottom.
Does this contribute to the phenomenon polarity?
Yes.
Okay. I didn't know if it goes beyond water.
Yes. Yeah, it does. So there's a lot of other molecules. That's what we're talking. That's what we're talking about now.
Isn't delta a triangle?
Capital delta is a triangle. That's a lowercase delta. Yeah. So the capital delta means like a full change, and lowercase delta means a little. Yeah.
That makes sense.
All right. So that gives rise to something called polarity. Polarity means partial separation of plus and minus. So you've got, if something is polar, it means it has 2 distinguishable sides. So in this case, a plus side and a minus side. And if you have a molecule that has that, it's called polar. So how do we decide that? Like, how did I know that fluorine was going to pull those electrons more than hydrogen?
Who's going to count electrons in this?
Sort of. It's actually more of an inherent property called electronegativity. Let's spell that. negativity.
Each element has its own, like,
Electronegativity. Yep. Each element has its own electronegativity, and that is defined as the ability of an atom to pull electrons toward itself in a covalent bond. So not just like any electrons in the world are going to get attracted to this thing, but when it makes a bond, the electrons in that bond are more attracted to something with a higher electronegativity. The book has a table of these, so we'll just steal it for our notes. So an element with a higher number that's bound to an element with a lower number, the one with the higher number will pull the electrons toward it. That's what that means. So if we have like an HF bond, H is 2.1 and F is 4.0. So that means the electrons will get pulled more toward the F. Now you don't have to remember these numbers, I would give them to you. But a lot of times we don't even need the numbers because we can look at the overall trends. So what you see there is electronegativity increases as you go to the right. And that's true across all the rows. And then it also increases as you go up. I don't know why they did. I think that was kind of confusing. Why would they say it increases this way and then decreases? Why would you just say increases this way and increases this way? But the way I remember it is fluorine is the most electronegative element. It's got the highest number of any of them. Yeah. So all of the other numbers kind of go up toward fluorine. You see that? Everything kind of gets bigger as it approaches fluorine, since that's the most electronegative.
How do you know it's like where it's at? Like as far as like, looking at the period table and knowing like the number of where it falls and all that jazz.
Sometimes you don't, and you just have to look it up on the table. So when you're comparing within the same row or within the same column, that's when you can compare. So you can say like, okay, I know that electronegativity increases to the right. So if I've got carbon and oxygen, the oxygen is going to be more than carbon because oxygen's more to the right. So you can say that. But if I said between sulfur and nitrogen, like sulfur is more to the right, but it's also more down, so that's not easy to compare, so you need the numbers for that. Does that make sense? And then we leave off the last column, the noble gases, because they don't really bond, so we don't really worry about their electronegativities. And metals all have extremely low electronegativities, so we don't really worry about them because they're not making covalent bonds anyway. And so in fact, we can kind of generalize this and decide what's covalent and what's ionic based on this idea. And I caution you, it's not exactly right, but it's a good kind of a rule of thumb. And it kind of shows how they're not these easy direct categories that we might want them to be, but there's actually more of a continuum. So depending on the difference in the two numbers, that's the top of this table, the electronegativity difference. If it's 0, that means each element has the exact same electronegativity, like H and H, or O and O, or whatever. If they have the exact same, the difference is 0. So that's what we call a nonpolar covalent bond. It's the electrons are equally shared across both atoms with that bond, and you'd have something like that purple blob. If you have a difference that's greater than 0.4, we start to call that polar. Why 0.4? Well, somebody decided that. It's more about how the molecule behaves and what that ends up doing experimentally. But and of course it has exceptions, but we can say 0.4 is a good spot to draw that line. Greater than 0.4, we're going to call that a polar bond, and the electrons are shared unequally, but it's still a covalent bond. They're still shared electrons. And then once you get over a difference of like 1.8, you're not really in a covalent bond anymore. You've actually taken those electrons from one atom and put them on the other one. And that's what we call an ionic interaction. Now, like I said, that's not totally right because ions, we can measure for ionicity, for like how ionic something is, like whether it conducts electricity or not. And sometimes something looks ionic from the difference in electronegativity, but it still doesn't conduct electricity. We know that that's not really ionic. So there are some things that don't quite work, but it's a nice way of summarizing what this effect is and what's really happening. So let's try that. Let's look at some different types of bonds, and you decide if they are polar or nonpolar. So we decided this one was polar. The difference in electronegativity is 1.9. Let's look at some other ones. CH, NO. Yeah, that's fine. PO. So see if you can quickly calculate those out and decide if each of those bonds is polar or nonpolar. So you're going to look up both numbers, both electronegativity numbers on the table, find the difference in them. If it's greater than 0.4, we call that polar. If it's 0.4 or below, we call that nonpolar.
Do you add them up?
Subtract the difference. Or another difference in the two numbers. All right, CH, did you get polar or nonpolar? Nonpolar, right. Because the difference is what? 0.4?
Wouldn't that be polar covalent then?
No, that's the number that makes it nonpolar. So 0.4 or below makes it nonpolar. Above 0.4 makes it polar. So this one, even though it's really close, we're going to call that one polar.
I said delta was the sign that was had like an 8.
Yes, this is a uppercase delta. Means like difference. Like a capital letter versus a lowercase letter. That's a math thing. That's not a chemistry thing. Sorry, I should have explained that. The uppercase delta, meaning a difference in two things, is a math thing. And so then PO is a big difference, with that difference being 1.4. So that 0.4, 0.5 line, like, you're probably not going to see a big difference in behavior between those two types of bonds, but enough that it may be significant. Okay, so now we've got polar bonds. The next thing to do is to decide if a molecule that is made up of polar bonds is itself polar. So these are talking about individual bonds. What about if you put all those things together and build a molecule what happens then? What do you have? Do you have something that's polar or not? Let's see how that works. So just like a bond, a polar molecule is one where the negative charges are on one side, or more of the negative stuff is on one side, and more of the positive stuff is on the other side. And to figure out if a molecule is polar, we look at the individual bonds, we kind of add them up in this special way, and then we decide what's going on with the overall molecule. So let's look at water. Water looks like this. And by the way, we're skipping the section in chapter 6 of how to decide what shape a molecule is. We're skipping that. So I will always tell you what shape the molecule is for what we're going to do now. So this is what water looks like. It's a bent shape, kind of looks like a V or upside down V, depending on how you draw it. And to decide if water is polar or not, we're going to look at the individual bonds first and decide if they are polar or not. So what type of bonds is water made out of? OH, right? So we would go back up to the table and say, okay, an OH bond, H is 2.1, O is 3.5. So that's a pretty strongly polar bond, right? Difference of 1.4. Okay, so a strongly polar bond means that there's going to be a lot of separation of charge. There's going to be positiveness over by the hydrogen, and there's going to be negativeness over by the oxygen. The electrons are going to be pulled more toward the oxygen because of oxygen's higher electronegativity. And that's going to happen on both sides of the molecule. Does everybody see that? How that bond, those individual OH bonds are polar. The electrons get pulled more toward the oxygen, and so the oxygen is going to be more negative, whereas the hydrogen is going to be more positive. Okay, so can you see a positive and negative side of this molecule? Where's the positive side? The bottom, right? So we could draw a line through this molecule, like around here. And we could say the positive side is below that line, and the negative side is above that line. And so that tells us this molecule is polar. It has a positive side and a negative side. And that means it is polar. Let's look at some molecules that have polar bonds but are not polar, and what makes them not polar. Let's look at carbon dioxide. Carbon dioxide has this shape. So it's straight across. So we look back up at the table. Is a CO bond polar?
Yes.
It is, yes. So that means that once again, we will have a separation of charge where there is negative on the oxygen and positive on the carbon. Same thing on the other side. I could have drawn that up on the same side too.
Why is the O negative again?
Because it's more electronegative. It has the higher electronegativity. It's closer to fluorine on the periodic table. So that's going to pull the electrons more toward it, making it more negative. So now, because this molecule is straight and not bent, something different is going on. You can't draw a line in that molecule and make a positive side and a negative side. You see that? Because the negative stuff is on the outside and the positive stuff is on the inside. So it no longer makes sense to cut this thing in half and have a positive and a negative side. It's like the two sides cancel each other out. So the overall molecule of carbon dioxide is nonpolar. Even though it is made up of polar bonds. So let me see how I can. A CO bond is a polar bond. But when we put that together in this particular shape in the molecule, it doesn't end up having a positive side and a negative side. So the molecule as a whole is not polar. There's another way to do this. That sometimes is helpful, sometimes is not. I like the just drawing a line through it because that seems easier to me. But in some cases, when the molecule is more complicated, you can't just do that. So what you do is you draw little arrows that represent the polar bonds, and you add them together like vectors. So you say, like, in water, you'd say, okay, here's one bond is going from positive up to negative that way. And the other one is going this way. Positive to negative. That's what that little positive on the tail means. So if you add them together, you've got this plus this. So your overall polarity is this. You like that way? You guys do like vector addition in physics and stuff? Haven't done that?
I'm sorry, we did
No?
physics one?
I don't know.
No.
No? Okay. Or math or whatever. Okay. So don't worry about that. Don't do that way. Stick with the line then. That's fine. The point is to decide whether a molecule is polar or not. Doesn't matter what mechanism you use to get there. All right. So let's practice this and let's try it on some different molecules before we move on. So we're going to look at SO3, which has this shape. It's like the S is in the middle of a triangle and the O's are all on the outside. And then I want to look at another. Oops. Before I draw this one, the shape that arises from 4 different atoms being connected to the center is something called a tetrahedron. It's a little hard to draw in 2 dimensions, or it's hard to kind of see in 2 dimensions if you haven't seen it before, because it's really a 3-dimensional shape. So I want to pull up this other program to show you this. Okay, sorry. So this is what the Ch4 molecule looks like. If you connect 4 hydrogens to a carbon, you get this shape. And this shape is called, it's called a tetrahedron, or a tetrahedral shape. There is a shape called a tetrahedron. It's kind of like a pyramid, but with a triangular base. That's where that name comes from. So you could imagine this is in the middle of that pyramid, and the H's are at the 4 corners. And everything is equally spaced and equally angled in this shape. We often draw it. Try to put it in a nice spot here. There. We often draw it kind of like this. So let's put this up here for reference. That word again is tetrahedral. And this is actually where the water molecule comes from. The water molecule is like half of that. And the way we draw this is to put that carbon in the middle. And then these 2 things coming off the side. And the other 2, one of them is kind of coming out at you and one of them is going back. You see that? How one is kind of in front of the other one? The way we express that in 2 dimensions is we draw a wedge shape to show that one is coming out at you. And we draw a dash shape to show that one is coming back. So if you see that kind of notation, this is the type of shape that we're that we're showing. Well, you don't have to know the, yeah, right. You don't have to know the, like how to determine what shape a given molecule is. I'll give you the shape. But if I gave you something like that, you'd need to know what that looks like in 3 dimensions. Yeah. To see that tetrahedron again, it's like this kind of, if you imagine. This kind of a shape. With that gray ball in the middle, and then those white ones at the corners of that shape. Okay, so in this particular example, I didn't use all H's, so I'm going to change those to CLs. And the other example I gave you would have the same shape, but a CL on every corner. Like that. So now that we're looking at these shapes, see if you can make some decisions about whether or not those molecules, those 3 molecules, would be polar. So you have to look at the bonds first, and then the overall shapes, and decide if they have a positive side and a negative side, or if they're more evenly distributed all around the molecule. Yeah.
For the CH2Cl2,
Yeah.
would Cl2 be plus for the electronegative?
Let's look it up. Well, so we would look it up. The a CCl bond, the Cl is higher than C.
Then the C would be-
So the Cl gets the negative, and the carbon gets the plus.
And then the hydrogen would get a plus also?
No, the hydrogen and the carbon would really get
Oh, so
nothing
you
because
base it
it'd be
off
the same.
Carbon?
Because it's about the bond, the individual bonds.
Okay,
So, like-
whatever's in the middle and what's around it?
Yeah.
Okay.
So let's look at these. So that's right. That's the first step, is to decide where those positive and negative pieces are going to be. And that's looking at each bond, which of the 2 atoms in that bond is more electronegative. So like in sulfur and oxygen, you'd look up at the table, you find that oxygen is more electronegative than sulfur. If you didn't have the table, you could look at the periodic table and you'd see, well, oxygen is above sulfur. So we would expect, since they're in the same column, that oxygen is more electronegative. So we've got negative on oxygen and positive on sulfur. And since that's the same all around, we can do that all around. So now, if that's a flat triangle like that, is there a positive side and a negative side, or no? You're shaking your head. No, not really. It's kind of like that carbon dioxide situation, right? The negative is on the outside, the positive is on the inside. There isn't a negative side and a positive side. We can't say it's negative on the left and positive on the right, or it's negative on the top and positive on the bottom. It's negative on the outside, positive on the inside. That doesn't make for polarity. So we would expect that this is non-polar. If one of those oxygens were missing and it were SO2 bent like that, then we would say, yeah, it's polar, because the positive side on the S would be positive and the oxygen side would be negative. But we can't say that in this case. Okay, so moving over to the next one, CH2Cl2. We would look these up and see that while a CCl bond is considered polar, a CH bond is not. So that means that we would draw partial negatives and partial positives for the chlorine and the carbon, but we would not draw anything between the carbon and the hydrogen because that is a non-polar bond. So do you see a positive and negative side then on this molecule? You can, right? You can draw a line like right there, and the positives are all on the right side of the line, and the negatives are on the right side of the line, and the positives are on the left side of the line.
I'm sorry, what happens with the C and the H?
The difference in electronegativity is only 0.4, so we just call those non-polar, and they don't get a positive or negative. Because those are non-polar bonds. And we should write that here. The carbon and hydrogen bonds are non-polar.
Why are they non-polar?
Because the difference in electronegativity between C and H is only 0.4.
Oh,
So we do, in this case, we have a negative side over here and a positive side over here on that line. So we call that polar. And this is called dichloromethane or methylene chloride. It's a common solvent. It's kind of a dangerous solvent. And then the last one, CCl4, same shape, but with all chlorines all around. So how does that change things?
do you first add up all the CLs,
What do you mean add them up?
like, the 3.0 for electronegativity?
No, because you're looking at each individual bond. So you're saying like this bond is C and Cl, and then this bond is C and Cl, and this bond is C and Cl. So if you find that there's a polarity between C and Cl, that applies for all the CCl bonds.
Okay.
And that is true in this case. So all of these are going to get a negative to the chlorine and a positive to the carbon. So what do you think? Is that polar overall or not? It's not, yeah. Again, we don't have a positive side and a negative side. We have negative on the outside and positive on the inside. So if you're seeing a pattern here, these highly symmetric structures, when they have all the same kind of thing, they're usually going to be non-polar because the charges basically cancel each other out. And you don't have a positive side and a negative side. So this one is also non-polar. Okay, so that was a lot. We put some covalent compounds together. We looked at the bonds. What does it mean for something to have a covalent bond? We then put them in a large molecule, looked at some shapes, and decided, is this overall molecule going to be polar or non-polar based on the polarities of the bonds? So the final step here, the final piece of this, the whole point of all this, is what are the physical consequences of what we just talked about? That is, what does it matter if a molecule has a polarity or not? And how it matters is how the molecules interact with each other. And the fancy word for that is intermolecular forces. But what we really mean is how molecules interact with one another. So what happens when two molecules meet, or when a large sample of molecules is interacting with each other? Well, as it turns out, the key difference in how molecules will interact with each other is whether or not those molecules are polar. So that's why we spend all this time deciding whether or not the molecules are polar. When they are polar, whether or not they are polar has big consequences on what's going to happen when they get together. So we're going to separate that into two categories. And first, we're going to talk about what polar molecules do, and then what nonpolar molecules do. All right. So if you think of polar molecules kind of like magnets or something, if you line up a bunch of magnets, what happens?
They will attract to each other, connect them together.
They'll kind of like attract or not. What happens if you have them oriented the wrong way? They'll push away. So depending on how they're oriented, they'll either attract each other or they'll push away. You can think of molecules like that, but they have free range of motion in whatever they're in. So they're always going to try to line up. That's basically what is happening. So if you have some sort of a polar thing, and we'll just say the thing is a blob here, we'll just express that as a blob. But if you have a polar thing that has a positive side and a negative side, another polar thing is going to want to line up with it in a particular way. So maybe it'll line up over on this side, and it's going to kind of go backwards, right? So the positive and negative are with each other. You might get another one over here. Whatever they do, they're going to line up so that positives and negatives are together. That's what polar things do. And that's what polar molecules are going to do too. So if you have something like let's say HCl. HCl is polar, has a partial positive on the hydrogen and a negative on the chlorine, so definitely a positive side and a negative side. That means that you would expect these molecules to kind of interact like this. So that the negatives go with the positives. Now those things aren't going to be as strong as like ions because these are partial charges, not full charges. So they're not going to be as strong of an interaction as ions, but there's still going to be some interaction there. They're going to attract each other because positive and negative attract each other. So the positive side of one is going to attract the negative side of the other. And these types of interactions are called intermolecular forces, that is, molecules attracting each other. And the specific name for this type is Dipole-Dipole Forces. Dipole is another name for a polar molecule, like dipole. It has two poles, a positive and a negative. So a molecule with a dipole, meaning a polar molecule, is going to attract other polar molecules, and they're going to orient in such a way that the negatives and positives are lining up in that way. Now, whether it's in a straight line or whether it's more like what we drew in the green blobs, that just depends on the compound. Different molecules will align in different ways, but they will align in some way that maximizes the negative and positive attraction. So these types of forces exist in all polar molecules. So that's one type of force that you can have with molecules interacting with each other. Those are called dipole-dipole forces. And those happen in polar molecules. Now, in some polar molecules, you get a special extra kind of interaction. So let's say you have water. Water is going to have a very similar type of thing going on. You've got negative on the oxygen, positive on the hydrogen. So you're going to have those same kinds of things happening. The negatives of one attracting the positives of the other. But this one is special. The name of this type of a force is hydrogen bonding. And this is a terrible, confusing name. Because it is not really a bond. We just spent all that time talking about covalent bonds and having electrons in each other's valences and stuff. That's not really what's happening with a hydrogen bond. But it's called hydrogen bonding. So I'm sorry for the confusion. It's not really my fault, so I shouldn't really apologize. Somebody else came up with it. But it's called hydrogen bonding. But we have to keep straight that it's actually a type of intermolecular force. It's actually a way molecules attract each other. It's not a bond inside a molecule. So what is that and how is it different? Hydrogen bonding is extra strong, so much stronger than a standard dipole force. And it only occurs with certain bonds. Only NH, OH, and FH bonds. Those are the atoms that are most electronegative, N, O, and F. So only when they're bound with hydrogen do you get this special scenario that leads to this special kind of force called hydrogen bonding. Now, why is that so special? Well, because as I said about the strength, water, for as small as it is, really should not attract each other as strongly as it does. There are no other small molecules that attract each other as strongly as water does to each other. In fact, there's nothing even close. Anything else that's as small as water is not a liquid at room temperature because it just doesn't attract strongly enough. So the fact that water can do this hydrogen bonding is one of the things that's just responsible for us even being here. That water can be a liquid at these sorts of temperatures is unusual for that type of molecule. And it's because of this extra strong interaction between water molecules. All right, so that's the interactions between polar molecules. If you've decided that your molecule is polar, then it can have either dipole forces or hydrogen bonding or both. It only can have hydrogen bonding if it has NH, OH, or FH bonds inside the molecule. The other category are the nonpolar molecules. Nonpolar molecules only have one kind of force. And it is called dispersion forces. And these forces are pretty weak. compared to the polar forces, which makes sense. These are non-polar molecules. They can't have as strong of forces. So what are they? Well, I don't want to draw it because it's kind of complicated. I'll pull in a picture from the book. Maybe they'll do a better job. Yeah, here it is. Let's think about, is that too small? It's too small. So think about nonpolar molecules that you might know. CH bonds are nonpolar, so anything made from carbon or hydrogen is nonpolar. So take something like gasoline. That's nonpolar, mostly octane, which is made of carbon and hydrogen. But it's a liquid, right? So something is holding those molecules together. If it weren't, it would just be a gas. There's some force there. And that force is called dispersion forces. So how do you have a force holding molecules together if there's no polarity? There's nothing to hold them together. This is what happens. We look at the atomic level, that you've got your nucleus in the middle and the electrons can be wherever on the outside. We've talked about that. Once in a while, just depending on random chance, the electrons happen to be more on one side than the other. Because if they're just wherever, sometimes they're going to be more on one side than the other. At that instant that they're more on one side than the other, there is what's called a temporary dipole. So as soon as they end up on one side, there's a little bit of a negative charge on the side that the electrons are on, and a little bit of a positive charge on the side that they're not. And that propagates across molecules. So sometimes these are known as induced dipole forces, because once one atom's electrons get a little bit lopsided, that causes everything around it to get lopsided too. And that's these dispersion forces that hold these things together. These very slight differences of electron density, so electrons being a little bit more over on this side of the atom versus that side of the atom, causes this whole thing to happen where you end up getting this attractive force. It's a weak attractive force, but it's an attractive force nonetheless, and it can hold things together. As you get more atoms in there, it gets stronger. So it gets stronger as the molecules get larger. The more atoms you have interacting like this, the stronger those forces are going to be. So that's why if we look at our carbon and hydrogen molecules, known as hydrocarbons, the small ones like methane, ethane, propane, butane, those are all gases at room temperature. But then as you get bigger, hexane, octane, which is gasoline, those are now liquids because now they're big enough to actually attract each other. And if you get really big, you've got waxes, stuff like paraffin, like candles. That's made out of non-polar molecules, but they're so big that they attract each other enough to become a solid. So that's the dispersion forces. All right. So the point of all this is everything we've done today, we should be able to decide if a molecule is polar, judge the strength of its intermolecular forces, of its attractions, and then make some conclusions about its physical properties because of that. So let me show you what that looks like. Well, here, I'll just put this in the notes too. Sorry, that might be small. So there's melting points of some substances. Let's look at these different kinds of interactions and what that does to the melting point. So you've got ionic bonds, these super strong interactions between positive and negative ions. Melting points are super high. If you can't see that in the back, they're in like the 800s to 1000s. That's how many degrees it takes to separate these things away from each other because they're so strong. Then the next strongest is these hydrogen bonds, these special things that we talk about with water and other things. Water, 0 degrees. Ammonia, -78. These are the melting points. Is that right? I don't think that's right. But anyway, the water one is right. I don't know about the ammonia one. I think that's the boiling. I could be wrong. We can look it up. Anyway, it's not that important. Dipole-dipole attractions are not quite as strong. So you see their melting points now are lower. And then the dispersion force is even lower than that, again, depending on size. So the stronger the forces are, the more energy it takes to melt or boil something. So we can make some good guesses about what has higher or lower boiling points based on the types of forces at work in those molecules. And so some of the homework speaks to that. So let's practice what some of those problems might look like. The one thing we should be able to do first is to indicate the major type of attractive force. And we may need to know the structure sometimes, and if we do, like the shape, I would tell you. But for these, we don't. So let's take a look at it. What are the major type of attractive force that you think occur between particles of these substances? So NH3, what type of force is at work there? Hydrogen bonding, how do you know? Yeah, anything with NH is going to have those stronger hydrogen bonds. If we go back up to our list here, hydrogen bonding occurs with those NH, OH, and FH bonds. So when we see those, we know that's going to be those hydrogen bonds. So that's going to be number 3. We can also say, by the way, that this molecule would have dipole attractions, dipole-dipole attractions, and also dispersion forces, because everything has dispersion forces. But the strongest ones are the hydrogen bond, and that's the major type. That's what's most important in describing the properties of this molecule. All right, what about HI? We may have to check our chart for that one, right?
Non-polar.
Yeah, it's nonpolar. So what type of forces are at work there? Right, those are going to be the dispersion forces. Because if it doesn't have a dipole, it can't have the dipole forces. Can't have hydrogen bonding. What about iodine, I2? Well, is an I2 molecule going to be polar or not? Why?
Because its electronegativity is 2.5.
Yeah, but what's the difference in electronegativity between 2 iodine atoms? If those are the two that are bonded together? 0. So that's going to be nonpolar. So it's not the absolute electronegativity of each atom, it's the difference across the bond. So that's going to be dispersion forces also. And what about cesium oxide, Cs2O? What type of forces are at work there? First of all, is that a molecule? How do you know? It's not. How do you know? Yeah, because it's a metal. So we've got a metal and non-metal. So what kind of a compound is this? This is ionic because it's a metal and a non-metal. So that means this isn't going to have any of those. That's going to be number 1, ionic bonds. Those are ions interacting with each other, not molecular forces. So not a molecule.
So dispersion forces are.
They're the weaker ones for
one.
non-polar molecules, right?
And dipole. How do you know if it's a dipole?
If it's a polar molecule, like if you have a positive side and a negative side of the molecule. All right, let's try another one. Um, here's a good example of how we can apply this. Why is the melting point of H2S lower than that of H2O? And I can show you the structures. So H2S has the same structure as H2O, just with S instead of O. So that's H2S. That's H2O. So if you get a question like this, where it's asking about melting point or boiling point, what it's really asking about is these intermolecular forces. Which one has the stronger forces that are holding the molecules together? Not the atoms together, the molecules together. Because when you melt or boil something, remember, you don't break the covalent bonds. You just separate the molecules away from each other. So which one of these two is going to have the stronger forces holding the molecules together, and why? H2O is stronger?
Yeah.
Why?
Because it has the nitrogen bonding.
Yeah, so they're both going to have the same shape. There's actually a couple of reasons here. First of all, we can see that the OH has that hydrogen bonding. And when you see that, that's usually the end of the story, because those forces are so much stronger that that one's almost certainly going to have stronger forces than the other. The other question, though, is H2S polar? It's kind of hard to say. We got to look at the chart, right? That's not one we can just guess.
Is there a way to find the electromagnetic or the electronegativity just off of
No, not really. Sometimes, like I said, if it's in the same column or the same row, you can, because the ones to the right are going to be higher than the ones to the left, and the ones below are going to be higher than the ones above. But anytime there's like a weird comparison to make, then you can't really do it. So, yeah.
The SH
Yeah.
has a weaker electronegativity.
Is it what?
Weaker electronegativity.
Right. So the SH is 2.5 minus 2.1, which is 0.4. So that's a much lower difference in electronegativity. In fact, 0.4 is so low that we call that nonpolar. So we would actually say that this one is really nonpolar. The S was 2.5 and the H was 2.1. So the difference is 0.4. So yeah, nonpolar, not going to have very strong interactions. And in fact, that's true. I don't know the...
would it be dispersion forces?
Yeah, so that would have dispersion forces. Let's look up the melting point. We know the melting point of water. I don't know the melting point of H2S. Minus 82 C. So that makes sense, right? So the melting point of water is...
Is that because the electronegativity is lower?
Yes, so that's because the molecules can't hold each other as tightly, and so it takes less energy to break them apart from each other. So water is going to be, I guess I can't write anymore. Great. So water is 0 degrees C, and H2S is minus 82. So that big difference is because of the strength of those water forces compared to the strength of the H2S forces.
If something's nonpolar, you automatically assume that it's a dispersion force.
Right.
And then if it's hydrogen and oxygen, it's a hydrogen bonding.
Right.
And then if it's an ionic, it could be an ionic bond. So if it's none of those, would it be the dipole-dipole?
Yeah, if you can find it as polar, like let's say it has CO or something, like SO, something where it's polar but it's not OH or NH, then we can say it's going to be those dipole-dipole forces instead. Yeah. But that's a good way to think about it, because if you know it's nonpolar, it's got to be dispersion. If you know it's OH or NH, it's got to be hydrogen bonding. So anything else in the middle is going to be the dipole, probably. Yeah. Okay. I think it's a good place to stop. So work through the homework on this stuff. So Wednesday in lab, we're a little bit behind schedule. Wednesday in lab, we're going to be talking about equations, chemical reactions, different types of reactions. So if you want to read a little bit ahead into chapter 7, that's fine. If you don't, that's fine too. But the lab doesn't exactly fit with what we've been doing right now because we're a little bit behind, just to warn you on that.
How far in the 7 should we read? Like 7:22, 23?
Just like, let's see. Don't worry about read about, hang on, I can tell you. I forgot about that. Okay. So you want to read about, you actually want to skip the beginning and go into the chemical equations, which is chapter 7.3. But skip the math stuff at the beginning about the moles and molar mass. We'll do that on Monday. Yeah, I think that'll help you with the lab, like with the pre-lab and stuff.
I have a question.
Yeah.
About,
Oh yeah, I got that.